Yeah, now it's good.
Oh, great. Okay, so thanks again. Thank you for the invitation and the introduction. And today I'll try to give a tutorial on variational quantum algorithms. We find these algorithms quite interesting for various different reasons. One thing, the reason people are looking at these is because we want to answer the question, what can we achieve with NISQ devices, where NISQ stands for Noisy Intermediate Scale Quantum, meaning quantum processors or quantum devices that are not full error-corrected quantum computers, but they do have, you can run circuits on them. As time goes by, the circuits become longer and longer, and we can presumably do interesting things. Of course, a very important question is, can we reach quantum advantage for some practical problems of interest? And one of the important applications or potential area where we can show quantum advantage is quantum chemistry. So I'll talk about that quite a bit. And other things we could try to achieve is obtain useful primitives. I'll make it clear what I mean by that, but basically, in a nutshell, you can think of a piece of an algorithm or a gadget or some circuit that does a particular task that might already be known, so you might learn a better version of it, or you might have some unknown primitive you want to implement, and you might be able to figure it out variational. And then there's also more fundamental questions that go into kind of more quantum information question type of consideration. So what is the structure, features, and capabilities of the parametrized quantum circuits? How does information propagate? Things like scrambling, entanglement, spreading over a system, etc. I'm not going to talk about these things, but I just want to put them here in the list because people are looking at those as well. And then, while you can view variational quantum algorithms as some sort of learning or training circuits in a kind of broad view, there's also more particularly focused machine learning goals that people are looking into, and I'll try to talk about those in the end. So this is my outline. I'll give some general introduction, where I'll talk about general features, which are not focused on any particular one application. I'll try to list challenges along the way, and I'll then zoom into specific applications. I'll talk quite a bit about fermionic many-body problems, because it's probably where most of the work is being done and a lot of my own group's work. I'll talk about machine learning, and in the end, if there's time, I'll also talk about optimization. And yes, so first, let me start with a disclaimer. This is a really massive field, so I will miss things, either because I don't have space to put everything, or because I'm not aware of every paper in the literature, even important ones. So I apologize if I miss an important result from people, and if anybody wants to share with me their work, I'm very happy to to find out more work that's being done in this interesting field. And of course, I'm not an expert on every single aspect. I try to make this as broad as possible and as informative as possible, since it's a tutorial, but not every single aspect falls under my expertise. All right, so with these disclaimers, let me show you where this field started from. So there was this paper in 2014, which, while it's only 7 years away, given how many papers have come out since on variational algorithms, this feels like decades away in some sense, where this was a collaboration between the group of Jeremy O'Brien and Alain's group, where the variational quantum eigensolver was introduced for the first time and used for the first time for a simple molecular problem of simulating this molecule shown here using photonic qubits. Now, the premise, the idea of variational quantum eigensolvers is actually based on a very simple principle, the variational principle of quantum mechanics. And this is undergraduate material. And actually, I have here my own notes from my undergraduate, which I recently found, which is a 2-line proof of the variational principle. This is Greek, it's not equations, but the equations are over here. So it's a very simple principle that states that if you parameterize a wave function and you calculate the mean energy, then that mean energy will be bounded below from the ground state energy. So you're trying to change these variational parameters or even change the variational form such that you lower the energy as much as you can and ideally reach the ground state energy, if that's what you're looking for. So all variational quantum algorithms have this basic structure. There was this recent review, this is a collaboration between the Los Alamos group and Jared McLean, and I'll follow some of their way of presenting things. So I'm referencing their paper, their review, very nice review paper, where it's relevant. So the idea is that you have some kind of objective function, and that function, if you're talking about ground state energies, would be the mean value, the expectation value of the Hamiltonian operator. So what enters in the objective function is the operator which you will measure, and the state with respect to which you're measuring. So the state that you create on the quantum computer. And compared to the classical variational principle, the difference here is that you create this quantum state on the hardware. You parameterize it in a certain way. There's a very big body of work on how do you do that. And then you make measurements on it, which you feed into a classical computer, and that classical computer performs optimization. That way you update the parameters, and then you feed these new parameters into your circuit, shown in this feedback loop over here, and you keep going until you're happy that you reached, you minimized your cost function. And depending on applications, different things can come out here. So you might be looking for a particular energy, minimizing it. You might be looking for probability distribution, approximating some function, etc. So in some sense, VQAs can be viewed as training quantum circuits. So what would you want out of your objective function? You want it to be faithful. So these are the criteria that were put in this review, which I like kind of the way these are outlined, so I copied that part. So you want it to be faithful in the sense that you want the solution to be contained into that representation. You want to be able to measure it efficiently. This third point here may not always be satisfied. You can imagine counterexamples, but in general, you want your cost function to change monotonically as you approach the solution. And then you want your circuits to be trainable. So there's a lot of trainability issues that come here in this field, and I'll try to touch upon them in a few minutes. So the form of the objective function clearly depends on what you're measuring, whether it's your Hamiltonian operator or some other quantity, and the state with respect to which you're measuring it, and that's your objective functions shown here. The ansatz is the parameterized wave function. I already mentioned that, but you can see here a little bit more specifically what that means. You have some evolution operator here, which is your quantum gates, which are parameterized by theta. Theta is a series of parameters. So you can think of them as a vector, shown here as theta 1, theta 2, theta L. And most of the time, you need to find out both what U should be and what theta should be. So oftentimes when we say train a circuit, we might be thinking of training the parameters, but I'll take a broader view in this talk and also talk about training the actual unitaries. All right, so the objective function can be different, will be different depending on what you want to do. So of course it depends on the problems and sometimes there's an obvious choice. For example, if you're interested in physical problems, very often you're looking for total energy, the variance of the energy, so that you have an eigenstate. You might be interested in the total spin and other physical characteristics. For other tasks, you might want to achieve a particular state. So there you might be using the fidelity, the overlap of the state you're creating on your processor with some target state. And then for sampling tasks, you're often interested in creating some probability distribution, which is you can sample from by making measurements on the quantum processor. And for some machine learning tasks, the choice may not be as obvious as some of these above. All right, so I'll give you some general feel for the type of ansatz that people use. And when I zoom into applications, I'll give you more specific examples. So given that we're still at the NISQ era, quantum processors are still quite noisy. Circuits are shallow because coherence time doesn't let us go deeper. The circuit has to be such that it doesn't push the coherence beyond what the coherence the processor can handle. So ideally, we would want as shallow circuits as possible without, of course, sacrificing the exactness or the faithfulness of the objective function. At the same time, classical optimization is not infinitely powerful, and actually, if you have too many parameters, you will generally have issues with trainability. So there's also a consideration of not overburdening the classical optimizer either. And then finally, you need ideally to span the solution space, the part of the Hilbert space where the solution lives. So I have separated the possible ansatz that people use into different categories. So the first category I call problem agnostic ansatz. So these are ansatz that are mainly dictated, the first two at least are dictated by the quantum processor. So in some sense, they're the simplest thing you can do, given what the capabilities of the processor is. So for example, in this first schematic shown here, you have a layer of single qubit gates, and you will notice that the parameters, the thetas, enter only in the single qubit gate layer. And then these sandwich entangling gates. So all the 2 qubit gates are in the green layer here, and you alternate those. This is typically called the hardware efficient ansatz, and it was introduced, to my knowledge at least, in this Kandala paper by IBM. Then there's another ansatz that's commonly used. This is used in machine learning tasks often, which is quite similar in some sense to the problem agnostic. I'm sorry, to the hardware efficient, but its structure has more this kind of brick layer or tiled structure. So here, I'm not necessarily specifying separating the parameterization into single qubit gates and leaving 2 qubit gates unparameterized. But the characteristic here is that you have nearest neighbor interactions and you layer them, you kind of tile them in this pattern. So this second structure here has, gives some intuitive feel that this might be able to spread the information around enough. So to make the circuits kind of talk throughout, the qubits throughout the circuit to talk to each other enough through this kind of alternating brick layer pattern. So both of these that I showed you so far, I haven't told you anything about what kind of problems we're trying to solve with them. And there's nothing problem specific that enters. It's just a structure. And for whole bunch of different tasks, you can take these layers circuit structure and parameterize it and try to use it as your ansatz. And in principle, you could use it for any problem you want. It's quite generic. Then another commonly used ansatz is a unitary coupled cluster. This comes from the chemistry community. And if you see here on the schematic on the right, which is taken from another nice recent review, you see that this contains parametrized exponentiated operators, creation annihilation operators that are, if you look at the first layer and the second layer, this is the singles. I guess we don't have the double right here, but this is a single particle in the fermionic side operator. Sometimes this ansatz is called chemistry inspired. So in the sense that you're taking fermionic excitations and creating a unitary gate from your fermionic excitations. And then of course you have to translate that into qubit operators. I'll talk about that in a moment. So while this, you could argue, has some flavor of the problem coming in the sense that you're taking physical operators on the fermionic side, it still doesn't know if you're trying to solve molecule A or molecule B or a superconducting problem, etc. So I would also classify this as a problem agnostic ansatz, even though it is chemistry inspired. And there's a lot of literature on this, both from the classical quantum chemistry and the quantum chemistry community. All right, so in contrast to these problem agnostic ansatz, we also have problem Taylor ansatz, and you can also separate these in two categories. So the problem Taylor ansatz, as the name sounds, knows something about the problem you're trying to solve, more specifically, knows something about the observable you are measuring. A famous example is the QAOA, Quantum Approximate Optimization Algorithm. I'll go into this in the end if I have time. This was put forward in 2014, and it has an alternating layer structure, but every other layer is the exponentiated Hamiltonian of the problem. So the problem enters the problem Hamiltonian enters very manifestly into the ansatz there. So this is kind of a different, I'll say this is a different level of problem tailored compared to UCCSD. And then there's other versions of this, like the variational Hamiltonian ansatz, which is taking terms from the Hamiltonian and alternating them. And then there's also some work from my group that I'll talk about, where you can take the symmetry of the problem and encode that, take the symmetry of the problem or the symmetry that the wave function should have, and encode that into your circuit. Now, within the problem tailored ansatz kind of category, you can think of something that's even more tailored to the problem. And in this category, the ansatz is actually learned as the algorithm is run. So the ansatz is not predetermined as it is here in the previous page, but instead your quantum and classical computer collaborate to create the ansatz on the fly. And we have done a lot of work on this. I'll talk a little bit about our work later on. And also other people have followed up. There's a lot of kind of this adaptive process inspired work. And then there's also genetic approaches where you have some generations, you run the VQE, and then the outcome of the measurements tells you how you combine these generations and make circuits so that these are also changed on the fly, and they're also informed by your quantum classical device feedback loop. All right, now next I want to go to the third issue, the third kind of element of VQAs, which is the measurement. So we want to measure observables efficiently. Whatever problem we're solving, most of the time, 99% of the time, what we're doing is we're writing our observable into a set of Pauli strings shown here. So these are tensor products of Pauli operators with some coefficient over here. And of course, since there's many of these, you want to figure out every time you make a measurement, how do you decide which ones you measure and which ones you group together to measure. And there's been nice work in recent years on this problem. So depending on what your device can do, you want to do either single qubit measurement. So in that sense, you're kind of not measuring, let's say, the operator XX, but you're measuring the operator X on one qubit and then the operator X on the other qubit separately. At the NISQ era, that's usually what people do because a proper XX measurement or higher weight Pauli string is expensive. So most of the time, people just measure single qubits. But ideally, you would want to eventually do a multi-qubit measurement, in which case you want to group the Paulis into commuting sets and perform multi-qubit gates to rotate the basis in a way that now all these operators that are within a group or within a set can be measured simultaneously. And of course, if you do it this way, you require much fewer measurements. So this problem has been attacked by many different groups, and now based on the collective work of several different groups, there's very nice results in the literature. I'll try to summarize them through these references. But basically you can estimate, you can find the accuracy in estimating expectation value by looking at the variance of the observable. And then based on that, you can find what is the optimal measurement count. And of course, you don't know what state you're creating on your hardware. So you need to make some kind of average, the same way that when we calculate fidelities, we average over states. And then in this very nice paper by Crawford and collaborators, they find an expression for how to group. They find some recipes for how to group Paulis. And basically what you want to do is you want to maximize this quantity shown here. So basically the results suggest that you want to group commuting operators according to the magnitudes of their coefficients. So there's a recipe of starting with the highest magnitude coefficient, and then as you go down in magnitude, add commuting operators to the different sets. And in general, maximizing this function is NP hard, but this paper gives some heuristic approaches. And this is a table taken from this paper over here that kind of summarizes the different proposals in the literature of how you group Paulis to measure them and what's the gate count and the circuit depth, etc. So there's nice resources that I encourage people interested in this to look at, and there's also nice kind of math that enters in analyzing these problems. All right, the next thing you want to do is you want to measure gradients. So as in order to change your parameters in the appropriate way, you're measuring, of course, your objective function, but you also want to measure its gradient. And a nice thing about Pauli-like gates, and actually they don't have to be Pauli strings, they can be a bit more general, is that you can write them in a way shown here. And you can analytically find, this is a pretty simple calculation, that if you take the derivative of the objective function with respect to one of the parameters that appears in your gate, so this is your objective function, this is given by this difference where you're running your circuit at the parameter shifted by this quantity shown here, and then shifted the other way, and you're taking the difference. This is reminiscent, when you look at it, to finite differences, but this is actually exact. So this is the exact derivative, and it actually holds for a class of operators. And there's recently been some generalizations where you can use some stochastic version of this for when you don't have the conditions satisfied, Pauli or Pauli-like operators. So here the condition was that you need to have two distinct eigenvalues. But for operators that have a more general spectrum, there's nice work by Crooks and Banking Crooks as well. And more recently, there's also some work on a similar parameter shift rule for in the case of non-unitary gates. All right, another important kind of concern for people is, of course, noise for variational quantum algorithms. And there have been many different approaches to mitigating noise. This is not where my own expertise lies, so I'm not going to go into too much depth in this, but there is quite a bit of literature and important works. So in this first example here, what you want to do is you want to purposely add noise by adding more gates which cancel out. So in the simple example here, you would add, instead of, you want to do 1 C0 between these two qubits, you'd purposely put 2 more. These, of course, ideally would multiply to 1, but in reality, they will add in some noise. So by adding more and more noise purposely, then you can sort of extrapolate back and go to the 0 noise limit, ideally. And this has been done by several groups, and notably by IBM group. And then there's more sophisticated techniques introduced recently by Bravi. I'm not going to go into details in this one, but I just wanted to put it here to make this discussion a bit more complete. Another thing you can do is you can enforce symmetries. If you know that the solution you're looking for has a certain symmetry and your measurement outcome doesn't have that symmetry, the simplest thing you can do is throw out the measurements that don't obey that symmetry. You could do something more sophisticated to try to actually encode the symmetries directly in your circuit. And you can combine these techniques as well. Okay, so the next step is, of course, optimization. Now you have measured, you have a way to update your parameters. And the challenges here is the measurement cost. To some degree, I addressed this in the previous few slides ago, where I showed you some results from the literature of how to group Paulis. And two big problems are, of course, the noise. So noisy optimization is hard, as well as the fact that the landscape, oftentimes, of course, this is very ansatz dependent or objective function dependent, but generically the landscape tends to be nasty. It tends to have local minima, and it tends to have what is called barren plateaus, which I'll talk about in a moment. So people have used various optimizers. Here you see in the original, this early IBM experiment, this is the optimization kind of process as the optimization iteration number changed. And this is an example of how a noiseless simulation would look like compared to the experimental case. So there's many optimization algorithms out there, you know, outside the quantum community, and these have been mostly imported to the quantum community. I'm just putting a list here. People have tried using various different optimizers. I don't think there is enough work yet to conclusively be able to say about which optimizers should be used. Every time you compare optimizers, your consideration might be different. You might be more interested in how it deals with noise or how long it takes, etc. So in comparing optimization strategies, I'd say that it's quite a subtle thing. There's a nice paper by the Google group, I believe it's this one up here, where they set their desired element to minimize the time it takes to do these tasks. And there they compared different optimizers for that particular kind of desideratum. All right, an important issue that enters variational quantum algorithms is barren plateaus. And what this is that the cost function can have gradients which vanish exponentially as the number of qubits increases. And of course, that's a big problem because if, as you increase the number of qubits, your landscape looks flatter and flatter, then your optimizer has nowhere to tell you to go, and you're kind of stuck in this flat landscape, and that's the name barren plateaus. So you can see here by looking at in the figure on the right, the variance of the gradients for a different number of qubits. And you see that, of course, this is layer dependent. So as you add layers, which means you add parameters, optimization parameters, you get these gradients become smaller and smaller, and then they plateau out here. So if you look at a cross section vertically here, you will see that this decreases exponentially with the number of qubits. And on the same vein here, if you compare how the landscape looks for when you change two different parameters in a circuit, you see that the 24 qubit case becomes much, much flatter compared to the 4 qubit case. And the intuition is that barren plateaus come from too much randomness, and too much randomness means too much expressibility. So typically, if you're it's a little bit of a two-edged sword here. So if you want, on the one hand, your ansatz to be expressive enough so that your solution lives in there, or you maximize the chance that your solution lives in there. And on the other hand, if you make it too expressive, then you start having these serious optimization problems. In addition, noise can also cause these barren plateaus. There's a lot of literature recently, especially from the Los Alamos group. So there was a recent paper. This was a collaboration between, I believe, the Google group and Volkswagen group, where they proposed a possible remedy to this bar and plateau problem. And this was to enforce some structure. So the intuition is that randomness is bad. So try to de-randomize the parameters in your ansatz. So the solution they propose is to have this layered learning structure. So instead of, if you have a circuit that has this kind of natural layering that I showed you earlier on, instead of sending the whole thing, trying to optimize that, just optimize it in layers. And then once you optimize the first layer, use that as your initial guess for the parameters when you add the second layer. So that way you're putting in some structure, you're decreasing randomness, and in their simulations, it seems to be actually helping. So the success probability is shown here. There's many hyperparameters that enter here because it has to do with how many layers you keep. If you freeze parameters, how do you freeze them, etc. So I'm not going to go into all these details, but I think there's going to be a lot more work for following up on this. This is a relatively recent result. Okay, so now, after discussing kind of some broad considerations for variational algorithms, I would like to start kind of zooming into applications and more problem-specific questions and more show you some specific examples and results from papers. Maybe this is a good time for a question if there are any. Okay. Actually, I'm going to talk about this in a different order. So I will start from many-body problems, which are the most common. I'll switch to machine learning next, and I'll leave optimization last. So fermionic many-body problems are, of course, notoriously hard to solve. We don't believe they can be solved classically. People have not succeeded all these years. The reason is that the Hilbert space grows exponentially with the number of qubits. And there's many famous problems that people are trying to solve in different communities for practical and fundamental reasons. So strongly correlated molecules in chemistry, superconductivity, various types of dynamics in physics and chemistry, for example, catalysis, and this is a long list that's not exhaustive. So variational quantum eigensolvers, in this example for molecules, this is taken from a nice comment piece by Alan. It looks a lot, of course, like a variational quantum algorithm. It's the exact same structure. It's really the same algorithm, only that here, more specifically, you're focusing on molecular systems. Your objective function is the mean value of the energy most of the time. And what you're calculating in the end is energies of molecules, typically as you change the bond distance. And you can also find actually excited states by modifying slightly what I'm going to talk about. So there's been a lot of experiments. This is not an exhaustive list. But as you can see here, these are reasonably kind of small molecules. I believe people have done up to 12 qubits or so. I'm a little bit biased because my own work is closer to superconducting qubits. So all these results are from superconducting qubits. But there's also nice results from the trapped ion community and the photonics community as well. So in all these cases, they find ground states, or in some cases, excited states like shown here on the left, as you change the interatomic distance. So I'll try to explain what goes into these types of calculations and experiments. So for most of these problems, we start with a Hamiltonian in a second quantized form, which means that we have already picked some bases. And we have already calculated the Coulomb integrals. So that is done. It's a pre-processing step. It's done classically. Particularly chemists have tables with these numbers that we can use. And of course, since this Hamiltonian is written in terms of fermions, it contains the wave function should contain the antisymmetrization property. So under the exchange of two electrons or two fermions, you should obey these anti-commutation relations shown here. So these are the creation annihilation operators. And in the mapping of fermions into qubits, you need to worry about this. So qubits are distinguishable. They're sitting on specific points and they can be individually addressed, and you're not going to confuse the one qubit with the other. They don't have exchange interactions. I should make a parenthesis here that there exist some systems where you can actually activate that exchange in order to do a gate, but I'm gonna ignore that in this talk. So you want to basically artificially have impose on the quantum platform the anti-symmetrization property. So what you want to do is do a mapping such that, for example, when you have a raising or lowering operator on the qubit side. Oh, I should first say, I'm sorry, I should have said this first. So in the rest of the talk, I'll be focusing on the so-called Jordan-Wigner mapping, where you map the zero state of a qubit. This is kind of a natural mapping because there's a binary sense to the qubit. It has two states, and there's a binary sense to spin orbital. It can be occupied or unoccupied. So this is the most kind of obvious thing you could think of, to label, to map an unoccupied orbital to a particular orbital maps to a particular qubit. The unoccupied state maps to state 0, and the occupied state to state 1. And of course, that misses, if you just do that, then you're missing this exchange property. And to impose that, you want to add Z gates, Z strings, such that the minus sign that comes from switching to operators, to fermionic operators, is carried on into the qubit Hamiltonian. So basically what you want to do is you want to map the creation annihilation operators on the fermions to raising lowering operators on the qubits up to these Pauli strings here, which are Z strings of all the qubits that are occupied prior to the one you're addressing. So in the second quantization approach, the fermionic statistics are entirely carried by the Hamiltonian, not by the state. So the state, unlike you would have in an actual wave function of fermions, the state itself is not anti-symmetrized here. Okay. I think there's a question, but I cannot see it. So,
should I read it? The question, Sophia?
Yes.
Should I read the question?
Oh, sure, of course. Yeah. Yes, please.
So it says, how do you evaluate the free energy which involves entropy, which is a nonlinear function of the density matrix?
I will get to that in the end. If I forget to, please remind me. But
okay.
I discuss a little bit these things later on. Yeah, so that's a good question. I'll try to address it later. Now, there's other mappings that are more complicated, and people are still coming up with different mappings. I apologize, I should have had references here. Yes, so now for fermionic problems, you have two, I'm kind of following this separation of how I classify ansatz into problem agnostic and problem specific. So I'll give you some sense of what people are doing with the problem agnostic first. So for example, in the IBM experiments with the molecules, they use this hardware efficient ansatz, which is alternating layers of single qubit gates that are parametrized with entangling gates that are not. And here there's some, the advantage, of course, that these are native gates in the processor. The disadvantages is that this is an ad hoc ansatz, nothing guarantees to you that the solution will live in there. And in your quest to actually find the solution, you might be trying to do it in an inefficient way, meaning sampling or spanning too much of the Hilbert space. And then, as I mentioned before, there's this issue for barren plateaus, which seems to be more prominent for exactly these types of circuits that are very random. On the other hand, we have this chemistry inspired, which is the UCCSD approach, which is exponentiating these this is a single particle operator, A dagger A, and the two-particle operator. These, of course, live on the fermionic side, and as we just said in the slide above, to make these Paulis, you need to have this long string of Z operators. So this gate here, when I translate it into a Pauli gate, it'll actually be a very highly non-local gate. It'll involve on the order n qubits where n is your system size. So translating these fermionic operators into gates, I mean, there's kind of two challenges here, right? One is that you have these multi-qubit gates by nature, and then you also have to trotterize them to break them down into smaller units, single and 2-qubit gates. And there's issues with doing this. There's a community that's focusing basically just on that. In the NISQ era, we would do a very rough thing. We would do maybe first-order trotterization. And first-order trotterization depends a lot. Its performance depends a lot on how I order these operators. And we have shown in this paper that sometimes you might not be able to achieve a chemical accuracy depending on how you end up ordering them. So this is, I just want to give an overview of this IBM experiment. This also feels like it was ages ago now. It's just 4 years. Here, the entanglement, this is alternating the hardware efficient ansatz. You see these layers are repeated d times. The entanglement here, it's quite interesting that it was done in a sort of analog fashion. It was not broken up into proper CNOT gates. Rather, they drove the qubits, but they let the native interactions kind of happen. And then since there's some room for doing that because there's this optimization step where you can absorb a lot of, you know, errors or kind of gates that would happen this way, that you wouldn't want to do this in a circuit where you wouldn't have this optimization step. And then, of course, they optimized and they get results like the one I showed you before. Now, the other category was problem-tailored ansatzen. One was introduced by the Troyer group, is somewhat similar, has some similar features as UCC or UCCSD. Here, they take pieces of the Hamiltonian. So they take the Hamiltonian, they break it down into different terms, and then you create these exponentiated versions of them, exponentiated gates, and you multiply them together, and you call that a layer, and then you repeat layers. And then in our work, we've shown that you can also enforce symmetries and create an ansatz which guarantees, if you know the symmetry, that the wave function that you're looking for lives in there. I want to talk a little bit about that. So here, you imagine you have your Hilbert space, and you have some symmetry subspace. And you know certain things about your system. So for example, you know how many particles it contains. If you know how many particles it contains, you wouldn't want to be searching in the whole Hilbert space, which contains other number of particles. You want to stay where you know that number of particles is here. And that's where your ground state is. So to do that, you can realize that if we do the Jordan-Wigner mapping that I showed before, instead of the 2 to the n minus 1 times 2 real parameters that you would need to parameterize an arbitrary quantum state. If you know that you have m electrons or m fermions in your problem, then you know how many ones your states should have that enter, the basis states that enter the wave function should have. So you only want to search linear combinations of those. And in that case, the number of variational parameters is actually much smaller. It's 2 n choose m minus 2. And here a key ingredient is this gate that was introduced by the IBM Europe group, Zurich group, where if you look here, this basis is 0001 1011. You don't mix the 11 with anything else or the 00 with anything else, but this mixes the 01 and the 10. So if you use a circuit that looks like this, we have proven where you have this A gates. What you do is you add NOT gates here so that you create the right number of ones. And then by alternating in this bricklayer fashion, these A gates, you know how many of these gates you need because you can count parameters. and you need as many gates as you can solve this equation, right? How many gates you need to satisfy the number of parameters here. And we have shown that this exactly expresses any wave function that has that symmetry. And this is pretty hardware friendly because it also only involves 2-qubit gates between neighboring qubits. And by design, it minimizes the number of optimization parameters. So we've done some simulations with IBM system, both with noise and noiseless, and also on the hardware, and we've seen these perform quite well. So compared to these native ansatz that IBM systems have, what we call ASWAP, the symmetry enforcing circuit, has the smallest number of parameters. This should be because by design it does. And in this case, it also happens to have a much smaller number of C0s, and it performs much better. These are only optimization errors because there's no noise. So what I mean here is that it's much friendlier to the optimizer if you only give it the parameters it needs and not unneeded number of parameters. Okay, now so far as problem tailoring goes, you can actually go even deeper in that direction. So on the one hand, we have the completely problem agnostic sort of random ansatz. In the middle, we have some that are problem tailored but predetermined, like the variational Hamiltonian ansatz and the symmetry enforcing ansatz. But what you can do is you can also ask your quantum computer to collaborate with your classical computer and to help you determine the ansatz. So in this sense, you can think of the quantum computer learning the ansatz as you go. And this is just a schematic where you start somewhere in the Hilbert space and then you iteratively go toward the solution. So there's a number of approaches. To my knowledge, the first such ansatz was introduced by our groups at Virginia Tech. This is a joint effort with Nick Mayhall at chemistry and Ed Barnes in physics. And I'll talk a little bit about that, as this was the first such ansatz. There's been many follow-up work since. So this is an approach where you actually ask the quantum computer to learn the ansatz. It's an adaptive strategy. It uses derivatives. There's variations that don't use a derivative to assemble the ansatz. And it's very problem tailored. So it knows a lot about your Hamiltonian or whatever observable you're interested in. So to do this, and also the nice thing is that because the ansatz is grown slowly, it's actually quite compact by nature. So you only grow it one gate at a time, and you might converge before adding too many gates. And the structure of the gates is similar to what I showed you before. Some exponentiated Paulis. Here I have assumed this is already anti-Hermitian, so I don't have a factor of I. I'm not fully consistent, I apologize with that throughout the talk, but whenever I have something like this, it's always unitary gates I'm talking about. So an important ingredient that enters here is the operator pool. It's a set of gates that you allow your circuit, the circuit you're training, to use. So there's a question, of course, how do you select this set? I'll get to that. But then once you have selected it, how do you decide which gates to append to your ansatz? And the idea is to use a gradient criterion. So imagine that you have your reference state here. This might be the state you have grown up to that point. And then you add this unitary operator to grow your ansatz even more. And this is, of course, the objective of the cost function. And you take the derivative of this at value theta equals 0. And you end up, you can easily show that you end up with this commutator, the mean value of this commutator. An interesting thing here is that this thing is very similar to the parameter shift rule. It actually is equivalent to parameter shift rule. This is a new operator. It's Hermitian. So you can actually measure it on the hardware. So we imagine also this step eventually to be done on the hardware. So this is how the whole algorithm works. You start with this operator pool. You have some reference state. And then you select each operator and you calculate its gradient, which means the gradient of the objective function with respect to the parameter in the exponent. And you make a measurement, and whichever one is largest, you append that one. Now, if you have converged according to some criterion, then you say you're done. If not, you add this operator, you re-optimize all the parameters up to that point, and then you actually keep going. Without throwing out any operators, you test again. Now you have a new reference state, you select again the largest gradient, and you keep going, and that way the ansatz is grown. So I'll show you some numerical results on this. Here, we use the same operators as the UCCSD, so single and double excitations, and simulated 3 different molecules. These are all classical simulations: lithium hydride, beryllium hydride, and hydrogen-6, and compared adapt at the different thresholds. So this is where what value of the gradient do you stop at, to each other and to UCCSD, and to the exact solution. So because here all the curves kind of fall into each other, we look at the error on a logarithmic scale, and the UCCSD is the orange curve. And you see that other than the first kind of the roughest version of adapt, the other two do much better. Now I can also ask at what cost is that done, meaning how many optimization parameters do I have? UCCSD being a constant, a fixed ansatz has a fixed number of parameters, but you see that adapt is actually needs much fewer parameters in these two examples. And actually in the one case where it needs more, it's where UCCSD does not hit chemical accuracy. Chemical accuracy is basically the value of the energy, the error in the energy where chemists are happy. And we also compared to what happens if I scramble these operators. So instead of using the ordering that adapt gives me, what if I take the same set of operators, same pool, and just put random combinations? And we always find that the adapt criterion, the adapt recipe performs better. So here really, it does really look, and this is again logarithmic scale, it does look like this algorithm is training the system. There's something to be learned that it learns here. Of course, this operator pool is a crucial ingredient. And maybe I should go a little bit faster. So one question is, how do you choose this and how do different pools perform? So we've tried to use a more hardware efficient pool where we just use exponentiated Paulis with up to 4, weight 4. And we see that while you may need more parameters in some cases for these more hardware efficient pool, you typically need much fewer C-naughts, sometimes by orders of magnitude. So it appears that hardware efficient pools win. And then there's also nice follow-up work to this where they showed that you could actually, if you select the pool but in a way that enforces symmetry, you can beat the fermionic version on both counts. And an important notion is the notion of complete pools. So what guarantees you that you can get to the ground state? To guarantee that, you should be able to get to any real state. We're assuming here that we have time reversal symmetry. And the way to do that is to take the operators in the pool, take all their commutators and the commutators with those, etc., and make sure that if you apply each of them to an arbitrary state, you can get to any other arbitrary state. So you can get a complete basis. So we have shown in this work that there's a sense of a minimal complete pool. And very interestingly, this scales linearly with the size of the system. So this looks very promising in how feasible this algorithm is. And the other thing is that because it has this layered structure by nature, which looks a lot like the paper I showed you to avoid barren plateaus, it's most likely much more resilient to trainability issues, and that's something we're currently investigating. Now, there's many other problems that I don't have time to go into that people look, physics and chemistry problems. So for example, you can find excited states. You can calculate dynamics. That's a very interesting direction. Using a variational principle called McLachlan's principle that is discussed by the group of Simon Benjamin in these papers. You can look at open systems and scattering problems and many other things. So let me move to VQAs for machine learning tasks. This paper that I mentioned before has, again, a nice overview. So the things you can do is you can look at classifiers or create classifiers, autoencoders, generative models where you want to sample from some probability distribution, variational quantum generators, circuits that look like quantum neural networks. And also there's a big community that, of course, does machine learning for many body physics. I'm not going to touch upon that at all. So I wanted to show you one early paper on quantum circuit learning. So the idea here is you want to train your circuit to perform a certain function. And you want to have a way to encode your data. So the data is given by the set X. And there's one layer here, U of X, which encodes the data. There's different ways you can do that. So in some sense, this is an arbitrary choice here. So you take each qubit and you do a rotation on it. That's parametrized by this X, and this X is, of course, your data. So this is not something you vary. And then the tensor product structure of the Hilbert space gives you nonlinear terms. So that's kind of the nonlinearity comes naturally that way. And then you have some kind of cost function, which has to do, of course, with the training set, which is this yi and the function you measure. So you want to calculate this quantity and you want to minimize it. And you do that by adding here a parametrized circuit where all the variational kind of part of the circuit is carried. And what they do here is they measure the qubits on the computational basis. You have to repeat these measurements to average over them. And then you variationally update the parameters such that you minimize L. And you do this, of course, collectively for your whole training set. And then they have shown, these are all classical simulations, that you can approximate functions such as the sine function or the absolute value of X. And you can see here some results on that. Now here there's a lot of ad hoc elements, right? You don't know, is this the best way to encode your data, and what should this U of X be, and what should you measure here? What should the circuit look like? And these are, of course, really important questions if you want to use this for machine learning tasks. There's a very nice recent paper by Maria Schuld and collaborators, where they start to, looking into these questions in a systematic theoretical way. So the data encoding strategy determines the result. Their conclusions are here. The data encoding strategy determines what kind of functions can be represented. So you have this in these circuit learning tasks. Usually, there's an exponentiated Hamiltonian that creates the data, that encodes the data. So this is what is used here. So there's a lot of room for further work on this because this is a very specific choice of circuit. So for exponentiated Hamiltonians like this, which carry the data, the objective function can be represented as a partial Fourier series, meaning that it's not the full Fourier series, it's truncated somewhere. And what's interesting in this paper, they showed, just by making these very simple assumptions, that the spectrum of this encoding Hamiltonian determines the Fourier frequencies, and then the whole circuit determines these coefficients. So what I really like about this paper is that it's putting more kind of theoretical foundations to these machine learning tasks. And you can see kind of the conclusions here as you add elements to your circuit, how you can approximate, capture higher Fourier components and approximate functions better. All right, this is a huge literature, so I just selected a few things that have caught my attention, over the last year, a few years. There's a lot of work I didn't cover. I should just let me go back. So for each of these bullet points, there's many papers, and I won't have time. I'll make a comment about the generative models to relate back to the question about entropy. But other than that, I'm not going to be able to cover all of those. So I just wanted to give a flavor in this tutorial. But I just also wanted to mention some other learning tasks that kind of tie back into quantum information or quantum computing. So an important primitive in many quantum computing tasks is the swap test, where you use an ancilla qubit to do a conditional swap gate. And by measuring the ancilla, you can actually find how much overlap there is between these two states, the trial states over here. So a nice paper from the Los Alamos group trained the circuit to try to find, circuits that do this, but with fewer resources. And they came up with, or rather the circuit came up, the system came up with a result that indeed, this is just for a single qubit state here, has only 4 C nodes. I forget the exact count here, but it's larger. Interestingly, I think the authors didn't, when they were performing this work, they weren't aware that this was done by other people in 2013, just by hand. So the trained circuit actually found the recipe that was introduced in this earlier paper, which was not done using any kind of machine learning approach. Of course, this is cited in their paper, but I think that when they were first running their circuits, they didn't know about this results. It was actually found. Another interesting work is learning noise resilient circuits. So you're giving some noise model and you're training your circuits on this noise model so that then the circuits it comes up with have some resistance to that noise. And there's papers learning other types of primitives such as teleportation, etc. Again, this is an incomplete list. So I don't know if I have, I would ask the chair if I should talk about optimization.
Yeah, maybe you can wrap it up in the next 2 minutes.
Okay.
Then we have like 15 minutes for questions.
Okay, that's good. Yes. So just to make this talk more complete, I think it wouldn't be complete without mentioning optimization at all. So one type of problem people are also interested in variational quantum algorithm community is optimization. And here, the optimization task is related. It's a classical optimization problem. So you can map it to an Ising Hamiltonian. So in that sense, it's different. It's a Hamiltonian contained entirely of Z's. And it's been shown, it's known for a while that these types of problems can be mapped into different types of Ising Hamiltonians. So for this max cut problem where you have a graph and you're looking for a cut that maximizes the number of edges it crosses through, can be mapped onto this particular Ising problem. And there's the well-known now quantum approximate optimization algorithm, which was introduced by Variational collaborators back in 2014. And here, these people had worked on adiabatic quantum computing before, so this certainly has an adiabatic quantum computing flavor, because the idea is that you want to end up in the ground state of Hamiltonian like this, Hamiltonian C. And what you can do is you can start from a state that's easy to prepare, that is a quantum state that has superposition but no entanglement. And then if you were to do this problem adiabatically, you would want to switch adiabatically from Hamiltonian, this Hamiltonian B, which is just the sum of x's and has this ground state, to this Hamiltonian, which is your optimization Hamiltonian. And if you did this perfectly adiabatically, of course, you would stay in the ground state and you would go from one to the other. Now, this ansatz here, it's a parametrized ansatz again. You can view this like a trotterized version of this adiabatic process. And here you start with this reference state, which is the eigenstate of this Hamiltonian, and you alternate layers of the problem Hamiltonian and what they call mixer Hamiltonian, which is just exponentiated B. And then again, you want to minimize the coefficients so that you get the ground state. Now, one problem is that this problem has been shown to have a particularly bad landscape, so it has a lot of local minima. And one of the reasons, presumably, is that there's a lot of, again, structure to this. So one thing we have done is look at alternative mixers, not just us, but also other people, including the NASA group. And you can show that you can also introduce an adaptive strategy where you find the mixers in an adaptive way. And if you move away from single qubit gates only and allow for entanglement in the mixers, then you can get much faster convergence, shown here in the green. And you can do that with actually fewer C nodes. So this is another area where there's, I think, a lot of room to improve compared to kind of the original formulation of the problem. And with these adaptive strategies, we've taken the first step in that. There's also interesting physics here, because we have found some evidence that there's connection to the concept of shortcuts to adiabaticity. So it's kind of nice how adiabaticity comes back and the physics comes back. So the very last thing I want to mention before I conclude is that traditionally, when you hear quantum simulation talks, you often hear about analog simulation, which is what Feynman envisioned and what the quantum simulation community, such as called atom people, do. And there's the digital universal quantum computing community. But actually with NISQ and VQAs, this line is really blurred. And in many of the examples I already showed you, not all gates were proper gates. Some were Hamiltonian evolutions, and some were, pulses you optimize, etc. I'm going to skip the slide. I just want to mention we have some work where we directly optimize, throw away the circuit, directly optimize the pulse. So I'll skip through this, oops, and leave you with a list of recommended reviews on the things I talk about.
Okay, thank you very much for this great tutorial about variational quantum algorithms. So there was this first question about the free energy. Maybe
yes.
You want to take that?
So yes, you can actually calculate gradients with respect to the free energy, which does contain the entropy, like you said, which is a nonlinear function of the density operator. There's some very nice papers where they show how you actually can do that, the circuits that you need to do that. One is by Troyer's group, and another one by the Los Alamos group, I believe, where I think they did some machine learning task to actually find it in that case. In the Troyer group, I believe it was analytically derived. Hopefully that answers the question, but you can do that step on a quantum computer using multiple copies.
Okay, great. And then there's a second question by J. Löhnen. What do you really mean by learning the ansatz? To start this learning process, you need to feed the system something. Isn't this what you feed the system to start learning the ansatz?
Yes, so I do. I should, in my list of disclaimers, I'm not a machine learning person, so I do use some of the terminology loosely. We do not give it training sets, but we do ask it to minimize some quantity of the objective function, and in that case, it creates its own ansatz. So that's what I mean, learning the ansatz. Maybe, strictly speaking, it's not the best choice of words, but I'm trying to make a parallel to the fact that, a lot of this has a machine learning flavor, even if we don't use the exact same techniques.
Okay. I don't know if the people want to ask the questions themselves. I can also let them.
Yes, and I'll be very happy to continue the discussion on Slack if we don't do everything.
Okay.
So I could answer this question about RSPQ. These are just indexing different orbitals. So you can choose if you use, which kinds of orbitals you want to include in your problem, and I'm just labeling those orbitals.
Okay, that was that question. Is there any way? Oh, okay. If this recording can be made available. And can you briefly review and show again the reference of Benjamin's variational approach?
Yes, so there's, I should maybe clarify, there's an older paper that introduced this approach from, I think, the 60s. It's called McLachlan's principle. And in the Benjamin paper, I'm trying to find it now, they tailored it to a quantum system. So I think it's here. It's this one over here. Can you see my screen?
Yes.
Yeah, okay, great.
Drawn at quantum 3. Good. I think that's been, okay. That's been all the questions right now. So with no more questions, I would like...
A question.
Oh, there's another one. I was too fast.
Sorry. Yes, I raised the hand, but
Okay, Rafael is going to ask a question, and then there's another question in the chat.
Sure.
Okay, good. Thanks a lot for your talk, Sophia. It was great. So I wanted to ask you like a question that is maybe two questions in one. So recently there's been a paper on the archive by Bittel and Clich that were proving the MP hardness of training variational quantum eigensolvers. So not the problem of determining, but just the optimization problem is MP hard. And also like considering this, it looks like this kind of adaptive approach, like the one that you presented, it looks promising. But I was wondering, do you think it's the way to go to avoid getting the optimization problem too complex, and also and you think also there is a way of somehow forcing it, the operator building strategies that you're following to force, for example, to keep the ordering in a way that doesn't, that tries to avoid barren plateaus? And would you bet on adaptive EQE strategies, or do you think?
I am biased, but I would, because you can actually, if you do things systematically, and you can actually combine strategies, right? For example, if you enforce symmetries, then you're already limiting yourself to the subspace of the Hilbert space. You're already avoiding a lot of these complications. The adaptive strategy by nature keeps you to a compact ansatz. You can start combining these strategies. And I think that's the way to go, because most of these, I haven't read the paper you mentioned, I probably should, but most of these papers that talk about, barren plateaus or issues with optimization, trainability, most of them make assumptions that do not hold in these adaptive strategies and do not hold in the symmetry enforcing circuits. So there's a lot of you have to make some assumptions when you prove these things, and usually
yes,
they're
in fact,
random.
that was the case for that paper.
Yeah, they're usually random circuits that don't have, they have a lot of structure in the sense that they are alternating, but it's basically the same gates repeating typically in a layered way. And I think those are the ones that appear so far, based on all the works from various groups, to be the most susceptible to these issues. And in the end of the day, I think they are just unnecessarily long and elaborate on both. They overburden both the quantum and the classical computer. That's why we're focusing on these adaptive strategies.
Okay, thank you. So there's another question in the chat. So how much does the successful convergence depend on your initial guesses of the parameters, if it depends on all?
How much could you repeat?
So the initial guesses of the parameters. So
I see. So we actually initialize the parameters to 0. We haven't done a systematic study of that, but from just some tests, it doesn't seem to matter. At least, so far we're solving smaller problems. It doesn't seem to matter. One aspect that enters in this layered learning paper and also in our work is that every new operator, new set of operators, sees the optimized parameters from the previous layer. And it appears that helps, rather than just, all our tests indicate that this helps, and that other paper also finds the same thing from barren plateau point of view.
So you first optimize one layer, and then you add a second layer and optimize them. Okay.
We re-optimize everything. In our case, we re-optimize everything, but the initial parameter from the previous layer are kept, exactly. Yes.
Okay, as the initial guess. Yeah.
That's right.
And also, for like quantum chemistry, probably you use then Hartree-Fock or the. So
far, yes.
Yeah.
There's no, you could not. It's just that I think in many of these VQAs, you do the simplest thing you can. In some sense, that's what the hardware, efficient thing is, right? In the absence of having some clue to do something better, you do the simplest. So yeah, in that sense, the Hartree-Fock is the simplest thing you could start with. But you can imagine, I could say you can imagine starting from something that's like some tensor network or some classically found state that's even closer to the solution.
Yeah, but the problem then is normally that it's a superposition state then.
Right,
probably,
right. So then creating it. So yes, exactly right. So
you always have the trade-off that you
do
either you make your beginning very complicated, or you have to have a longer circuit.
That's right. And there's also the approximation that enters in trotterizing and creating gates. So yeah, we were taking the simplest approach of Hartree-Fock simple states.
Yeah. Okay, thank you. So I think there are no more questions. I think we've gone through all the questions. So thank you again, Sophia, for giving this really great tutorial. And if there are any more questions, you can contact her offline.
Absolutely.